Hello again and welcome to my science channel, and what we're going to do tonight is a bit of the reverse of what we did last time. Last time we looked at the charging of a capacitor, but today we're going to look at the discharging of a capacitor. So essentially what we're going to do is we're going to charge up this capacitor until it's full, which it is now, and that's reading cycling between 8.86 volts, cycling between 8.5 and 8.6, but that's on 8.86 at the moment. So what we're then going to do is we're going to disconnect the supply, or we'll switch off, so that's broken the circuit. We're going to take off the power supply, and then we're going to put a link in where the power supply was. So what we've got then is just a continuous circuit for the capacitor, and the only thing breaking the circuit is the switch. So this is the circuit that we have. We've got the capacitor, which is 470 microfarads, we've got the resistor, 15 kilo ohms, and the switch. We know the capacitor is charged up and is holding charge, and when we close the switch, that'll short out the capacitor and it'll slowly discharge. And what we're going to do is we're going to fill in this table again and then plot the results and see what sort of curve we get on the discharge. So with no further ado, after discharging the capacitor through the resistor as per this circuit, as we've already said, after 5 seconds we were down to 4.66 volts, after 10 seconds we're down to 2.54, after 15 seconds we're down to 1.38, after 20 we're 0.76, 30 pardon me, we were down to 0.24, 40 0.07, 50 0.03 volts, and finally after 1 minute it was 0.01 volts. Okay, so we plotted them on the graph, and that's this green curve here. And what you can see is that we've got an exponential curve once again, but going down discharging. If you remember, when we charged, it charged exponentially upwards, and now we've discharged it, it's discharged exponentially downwards. And we can try once again and predict this using a mathematical formula. And what we'll do is we'll try and predict it for 5 seconds. So we'll do a little mathematical calculation to see after 5 seconds if we are close to that 4.66 value. So looking at the circuit, what we've said is the V supply is 8.8 volts, 8.5 volts. The time is going to be 5 seconds. R is going to be 15 times 10 to the 3, and C equals 470 times 10 to the minus 6. Now what I want to concentrate on as well is how you actually input these into the calculator. So we can say voltage on the capacitor is going to equal V supply, so that's 8.85, multiplied by E to the minus, now let's put some figures in, 5, so because it's 5 seconds, over RC, which is our time constant of the circuit, and of course the value of the resistor and the capacitor. So that's 15 times 10 to the power 3 multiplied by 470 times 10 to the power minus 6. Okay, so let's take this step by step. So VC is equal to 8.85 times E to the minus 5 over, let's get a number for this. So when we type this in, we say 15, and it's not a multiplication, it's times 10. It's times 10 on the bottom, and some calculators you'll see an EXP button. So it's times 10 to the power 3. And then multiplied by 470 times 10 to the minus 6, because it's a microfarad. And that gives me a number of 141020, so if we add S to D, 7.05. Okay, so our next step then, we can say VC is equal to 8.85 times E. So we can work out this now. So we can say minus 5, minus 5 divided by 7.05. So that equals minus 0.70. And that's 709. So we'll say minus 0.71. Okay, now we're starting to get somewhere. So we say VC is equal to 8.85 multiplied by, let's get this number of E. Now if we look at our calculator, we'll have an E to the X. I can see that. Oh, there. So on this calculator, there'll be shift E to the X there, and it gives you that, and you put minus 0.71 equals, and I'll give you a 0.491. So we can then say VC is that multiplied by 8.85, and that equals 4.35 volts. And what did we measure it at after 5 seconds? We measured at 4.66. So measured at 4.66 volts. So that's not bad, considering the tolerance of the capacitor, resistor, etc. What we've measured and what we've calculated is quite accurate. Now, we did mention another formula as well. Q is equal to CV. So it would be nice to see at this voltage what sort of charge is there. So we actually measured 4.66 volts. So we can say Q is equal to the capacitance, which is 470 times 10 to the minus 6 times the voltage at that point, so it's 4.66. So we can say the charge at that point on the capacitor is going to be 470 times 10 to the minus 6 times 4.66, and that equals 0.002 coulombs. So that's a little bit on capacitors we looked at. So we looked at exponential charging, exponential discharging of capacitors, and how to calculate the number of coulombs of charge stored on the capacitors at any one time. I really hope you enjoyed that. I think I might do some astronomy next, some astronomical units and things like that, and then following that then we'll move on to some other electronic components like diodes and transistors. But anyway, during this crazy coronavirus time, I hope you keep your social distancing and all keep safe, and until I see you next, be good.